You're going to give us the homework today,
right? Oh, dang it! I forgot. The homework will be in the what's that word? Mailbox outside of my office. And give me about half an hour to enter the grades into Carmen. And then that'll be there for you to pick up. Sorry about that. I meant to do that this weekend and got distracted by emergency room trips. So today is exam and project problem question, right? So the written part, the written exam, for those of you taking it, will be basically the same format as the midterm, right? It should be it's not any longer, right? Even though there's an hour and 45 minutes to do it, I'm not going to add any extra length. So it will be well, I don't know how long it would normally take because no one actually finished, right? Like no one turned them in early. Everyone basically took the whole time. But it should be a little shorter time-wise than the midterm, but the same format, right? The material goes all the way through with creep only being covered conceptually, right? No quantitative creep questions. Gesundheit. So I guess we can start. Do you guys want to? Who has project problem questions, or I fielded some of those by email. So, Stan, do you mind if I share your updated? Okay. So, Stan made yet another improvement over Suprio's improvement of the Bishop Hill code. So I will post that, and if you haven't downloaded, so the one that's up there now reads the output from VPSC into the Bishop Hill directly, and then Stan writes out the effective stress, the stress state for each one, and the Taylor factor as well, or?
It was already in there.
Oh, okay.
You did all the work.
Maybe I missed
something. I just said it in the stress state.
Oh, the stress state.
Number.
Oh, okay. So which? Okay. So that's there. So any other project problem questions? Has everyone at least run it and make sure that it actually functions on your computer? Okay. Like with numbers?
Yeah.
Yeah, so it was also pointed out that at least in one of the versions, I forgot to change the input file from tensile to compressive, or compression to tension. So it doesn't matter because the way the parameters are set, there's no asymmetry. So you could just use just leave it as it is. So just run the input file that's given, and just plot the stress strain curve as if it was a tension curve. All right, the texture is random, so there shouldn't be any difference. The final texture would look slightly different, but okay, so questions on the exam?
I have a generic question.
Yeah.
On the amorphous formal homework for that chapter. So do you, what, you ended up asking us kind of do problems on our own.
Yeah, so the problems that we did in class, right, are we did that in lieu of a homework assignment.
Would you mind like reposting that homework set on the comments so we can actually?
Yes. Okay, so that is note for me. Okay, so post questions on amorphous. UOUS. Okay. So I have that note. All right. Any questions on content or structure for either the written or the oral? Yeah.
2 questions. So the first one, I guess, would be structure in general for the oral.
Well, so yeah, so it'll basically the whole range. Obviously, the oral is a half-hour time slot, right? So it's not as quantitative, right? What I'm looking for with the oral exam is understanding of the key, what I would say are the key areas, like how do you approach a problem, right? So the written part, any mathematics, is basically going to be kind of without numbers, right? So, coordinate transformation, right? You can write it down, in general terms, right? An eigenvalue equation, you can write it down in general terms. And that being said, that gets you most of the points on the written as well, right? So, it's not too much. The oral exam, to be fair, is going to be open notes, whatever you think you need, but you're probably not going to need it, and looking for the answer in your notes is going to eat up your half hours of time slot, right? Grading on the oral exam, I will be so that we have a record. I will be asking everybody if they mind me recording at least just audio, right, of what we say. This way, just in case a question comes up, right, or you feel that you have a yeah, right, if someone feels that they have an unfair grade, right, everyone has a right to a copy of their written exam, right? So if you feel, and it's the same thing, right, if you feel that your grade is unfair, if we make a audio recording, right, then you have a recourse to say, hey, I think I did much better on this. And instead of it being just my memory and your memory, then we can, right? I'm not, don't worry, I'm definitely not expecting that to happen. But I just wanted to let you know that I was thinking about this just for documentation purposes. But yeah, so that would be the general format of the.
When's the last date to change? I don't think I will, but when's the last date?
Well, I mean, it would have to be before the start of the written exam, right? I would say don't make a change before Wednesday. Before I wake up Thursday morning, because Thursday people have scheduled, right? Right. So, what's that?
I was just asking about how to set up the I forgot.
Oh yeah, I sent out there's the link on Carmen for the. And if those time slots are like filled up or there's not a good time, just we can work a little bit. So, are there any content questions? Oh, you're
Yeah, and that was the second one.
okay.
So the second one is on polymers, is on just the general loading and unloading. I'm still having trouble with some of the, when you unload it, the elastic part that unloads.
Are you talking about the viscoelastic
Yeah,
section?
viscoelastic.
Okay.
Yeah.
Okay. So
General.
yeah. So basically, right. So if it's viscoelastic, right?
The projector.
Oh, the projector's not on.
Turn it on. Weird.
Okay. So the projector will be on in a second.
The longer I hang up, the longer I have an issue, the longer I realize that Ben Franklin's statement is incomplete. There are three things in life that are certain: death, taxes, and misfunctioning audiovisual equipment.
Okay. Right. So basically, guess what you're getting at is the general regions, right? So you have you're going to have an instantaneous elastic response,
Yeah.
right? Right, we can pretend this is instantaneous, right? Just like we would draw the instantaneous elastic response of a metal, right? And then you're going to have a viscoelastic region, right? Right, where you've got a time-dependent response that is going to decay. The rate of strain is going to get smaller with time, right? And then you're going to have a unloading, which is exactly the same, right? Because it's linear, right? So you can think of this exactly as adding a negative load, right? This still, we can continue. We can say this, still continues out in an imaginary way, right? For ever and ever and ever, right? So that is still going. We can think of then this here adding an imaginary unloading and an unloading curve that goes imaginary asymptotically, right? The same, right? This is just adding a negative load, and the real load is the real response that it sees is going to be the sum of those, right? So this is asymptotically going to go to 0. So the important thing to remember is this curve here is exactly the same as this first part, right? And this here is the sum of these two imaginary curves, right? And that's why we can do the tabulated stuff, right? So if you have a single curve, right, where it has time and strain, right, and you have 0, 1 minute, 2 minutes, 5 minutes, 10 minutes, 15 minutes, 20 minutes, right? Right. If you have a table like this that gives the strain all the way out to long times, you can solve the loading, unloading, scaling, whatever, right? Because it's linear, right? Right, and you just got to kind of remember what the definition of a linear function is, right? So it's f of a plus b is equal to f of a plus f of b, right? And f of ax is equal to a f of x, right? And these two observations are what allow you to basically do this, right? right?
Yeah.
Is that what you were going for?
Yeah.
Okay.
Yeah.
Right, so, don't get lost in the details, right? Just think of this very, very simple picture, right? Because this will serve you much, right? This is, if this is all you get from viscoelasticity, I'm happy, right? Right?
Well, from the midterm problem, you also mentioned about the Boltzmann superposition. Can you explain a little bit about that?
Yeah, that's basically what this is, right? Just that you have to consider like the the function, the response, the time dependent response depends on everything that happened previously, right? So if your material isn't in this unrelaxed state, whatever you do, right, has to consider the previous. So here we've unloaded, right? But we have to consider that we already have this current load, right? That's going to continue on and on and on out to infinity.
I
Right.
wasn't just familiar with the term.
Yeah, and all as the Boltzmann superposition says is the deformation is a linear function of time and load, right? That's all it is there, right? Right, and you can tell, most viscoelastic things are not actually perfectly linear, right? But for a reasonable approximation and reasonable times and reasonable stresses. It's the same way most crystalline materials don't obey Hooke's law exactly, right? There's a nonlinearity to the elasticity because you have a nonlinear, an anharmonicity in your potential well. But for 99.9% of everything, we can ignore the higher order elastic effects, right? Same thing here, right? We can ignore the nonlinearities for most engineering purposes. Other content questions?
I have a question about the lattice rotation under tension and compression.
Okay.
So it seems like you have to rotate towards like the slip direction or away from it, but I don't like. So for FCC, it's easier to do, but for like complicated systems, I don't like. I can't verify which one is like which. Which direction should I go to? I mean.
Yeah. Okay. So now let's just think about this schematically. So here we've got a single crystal, right? And in general, right, the slip plane that's going to be active is going to be something like this, right? Okay. So as this slips, right, what are we going to look like? Right? Now you've got a shear here, right? You've got something like this with a step, right? And now, if you've got a whole bunch, you've got your crystal's not straight anymore, right? So now your load is offset from the axis of your sample, right? So you have a moment. Which way is this going to cause your sample to rotate?
So the slip plane goes closer to straight up and down.
Right. it's going to try and drive your slip plane, right? Yeah, this is going to, your slip plane is going to become parallel with your axis, right? So you've got a moment here that is causing a rotation like this, right? Right, so really simple physical pictures help sometimes, right? Try not to memorize facts like that, right? Right, because I'm really bad at memorizing, right? I can't do it. But just think about that. And the related question, right, about this stereographic triangle, right? Right. So what are these directions here? Right. The corners. Right. What's this corner going to be? 110, and this is. So that would be. This is 1, this is 011. Okay, yeah. I just wanted to make sure I didn't need a negative sign with the hand that I had, right? So this is the standard stereographic triangle, right? Remember, if we've got a load that comes in here, and I'm bringing this up because this was just on a candidacy exam the student had. A lot of trouble. Got there eventually, but so this question is fresh in my mind. Right. We have that rule of thumb for FCC about deciding what slip system is going to be active, right? Projecting across here, right? Which gives you 101, and projecting across here, right? Which, if this is 001 here, and this is 010, this becomes 00R1 down here, right? For deciding slip systems. But in reality, all you're doing is looking for the one that's closest to 45 degrees away from here, right? That's all that this little trick on the stereographic triangle works, right? It is doing. So there isn't a simple trick like that for lower symmetries, but you can still basically do the same sort of thing on the triangle by looking. If you know what your slip systems are, I can look for my slip plane that's within 45 degrees, right? And look for my slip normal that's within 45 degrees, right? And that's all that's doing, right? And then figuring out what's happening rotation-wise is much more complicated in lower symmetry, right? In an FCC intention, right? You rotate to this line, and then you rotate to a 211 type orientation. And in BCC, you've got a bifurcated, right? You have, depending on where you are, you got two slip systems that can be active. So it gets complicated, but this idea, it's still a quick and easy kind of visual for looking and saying, right? That's the beauty of a stereographic projection, is it allows you to visualize angles between planes, right? That's why it's useful, right? And so if you can calculate angles, right, you can calculate slip systems pretty easily. Other questions? Are you guys feeling fairly confident or fairly terrified?
What about like the Bishop and Hill maximum work versus minimum work? I don't quite understand why those are similar.
Okay, so okay, so yeah, and this is something I'm glad it wasn't 100% clear. I really tried to clarify this in the lecture as best I could. Okay, so you've got right, Taylor's concept of minimum work, right? Which basically says the minimum amount of shear that you have to do. So if you think in FCC, you've got 12 slip systems, all with about the same slip resistance. So what Taylor says is if you are trying to determine which slip systems are active, right, for a given deformation. Right, again here we're assuming a deformation, we're asking how do we accomplish that deformation, right? It says the combination of slip systems that gives you the minimum work, right, or the minimum for FCC, the one that gives you the actual minimum amount of slip, right, is going to be the active one, which makes sense, right? There's a, which path is, nature is really good at finding a minimum path, right? Right. Dislocations that don't have to be active are not going to be active for the most part, right? We want to, and so it's no deeper than that. Where the confusion comes in is Bishop and Hill have a maximum work kind of, what's the word I'm looking for? Principle, right? And principle, and I always have to double check and make sure I'm using the right principle. And the question that it's asking is different, right? The question is, for a given deformation, what is the stress state? Right? And so that's the key difference, is what maximum work is asking, what is the stress state that the grain sees to accommodate a given deformation? And here, the idea is the one that is going to maximize the work done, or the stress state that dissipates the most with the highest plastic dissipation, right? And it's equivalent if you think of force times, right? So from physics, work is F dot D, right? Right? The force times the distance it acts upon. How do you maximize this? Right? You align your force vector with the direction, right? How do we maximize the stress state? Right? What's our plastic dissipation? What's our plastic work? Right? It's this sigma with the strain rate. Right? So how do we maximize this? We try and align the directions of our stress to the directions of our strain rate. Right? And that's how we maximize the work done. And it turns out that these two are equivalent. When you have the stress state that does the maximum work, you actually do the minimum amount of shear, right?
It feels like this is an efficiency problem.
Yeah, it is. Both of them are efficiency problems, right? Just one is asking what's the most efficient set of slip systems to accommodate a deformation, and one's asking what's the most efficient stress state in my grain, right? In continuum mechanics, we call this enforcing a normality flow rule, right? That the directions of stress are aligned with your directions of strain, right? We know that's true on if you have a homogeneous body, right? But a crystal, your deformation can't be homogeneous, right? So what Bishop Hill says is, well, we don't have exact normality. Let's just get as close as we possibly can. Right? Does that hopefully answer your question?
Oh, yeah. That's clear.
Right? But yeah, there's no real magic there. It's just they're asking different questions, right? And unfortunately, has very confusing names. Right. So I mean, and remember. Both of these criteria are still not don't uniquely determine everything, right? There's still some ambiguity, right? Taylor there's possibilities of more than one equivalent solution, right? Bishop Hill doesn't tell you what's the proportion of the slip on each slip system, right? It tells you the stress state and it tells you what slip systems are active, right? But I might have 8 slip systems, but it doesn't tell me how the shear is broken up on those 8 slip systems, right? I only need 5, right? So anytime I have more than 5 slip systems active, I have a non-uniqueness in still have an ambiguity in my solution, right? That's why we use in crystal plasticity we use the power law formulation, right? Because that allows us to resolve that ambiguity, right? By having a rate sensitivity in it, because if you have to accommodate more shear in the same time increment, means you have a higher strain rate, and that slip system is proportionally more difficult to activate, right? So that's how a rate sensitive formulation resolves that ambiguity. But that's deeper than you need to consider here. Right. And again, this slide, right? If you kind of understand this slide, then you're as far for polycrystal plasticity, right? And the general notion of what a Taylor factor is, right? Because the Taylor factor is something that you can calculate from an EBSD scan, right? If you take your if you on the SCM and you're doing EBSD and you get a grain structure, right? I've got an orientation for each of these. In the TSL software, if you give it a loading direction, it will compute a Taylor factor for you for these grains. If you give it a strain state, right? So it basically the analysis software has a Bishop Hill calculation in it, right? It computes the Taylor factor, and then you can say for any given loading condition, which grains are going to be the easiest to operate, right? And so that's automatic, right? So it's a really useful kind of concept, right? Just being able to look at a polycrystal and say, which are my easy to slip grains, which are my hard to slip grains, where is deformation going to start, right? What happens if I have a hard grain next to a soft grain, right? You get a pile up, right? Potentially, that's what causes damage, right? Dwell fatigue in titanium alloys is caused completely by that, right? You get a cluster of grains that have the similar orientation, right? So you end up with like a millimeter-sized zone, which can be thought of as one grain. Then next to it, you have a millimeter-sized zone that has a different microtexture, right? And in the early 2000s, this was a big problem because they did put titanium into certain structural aircraft components and started seeing failures. Well, they performed really well in static and dynamic deformation tests. They performed beautifully in high cycle fatigue, but when you had a dwell fatigue where you take it up and you hold it a higher stress and then let it down, right? And you do this, it's sort of like on takeoff, flight, land kind of cycles. It had components that failed after, things that went to millions of cycles in high cycle fatigue, failing after a couple hundred cycles for dwell. And it's just because in here, right, you basically had a pileup that became kind of non-reversible, right? You had a hard grain next to a soft grain, and it allowed failure to occur.
When you calculate the Taylor factor, so if there is more than one slip systems, then how do you calculate it?
Well, for FCC, just assume that all have
same CRSs, but I'm asking is other slip systems and one other plane and other system.
Yeah, so if you're doing non-FCC metals, you need to give it the relative activity between the slip systems, between the slip modes, right? It's beyond right, beyond what we do here. But you can imagine, you've got a sum over the shear rates, right? It can weight those shear rates by how difficult the different slip systems, right? A CRS. You have the CRSS values for all of the different slip modes, right? But it's a kind of a subtlety, right? But it's not. If you really want to do it, I can have you write a quick Taylor model, right? Where you actually solve the rate instead of doing the Bishop Hill, solve the power law formulation, and then you have all the shear rates and the stress states, so then you can. It's worthwhile spending a day or two doing it once. Okay, any other questions? Okay, so I will see some of you Thursday. I'll see some of you Friday. Any other questions? Just I'm around all week, so. Okay.